Okay, take it away, Teamer.
Hello, everyone, and welcome to the Audio Programmer Virtual Meetup. The December edition today is the last meetup of 2021. It's again me and Josh. We are your hosts tonight. And we also have two wonderful guests, David and Jatin, who are going to talk to us later today about lots of interesting things. But before we get to that, Josh, how are you doing today?
I'm doing great. I am, for once, not in England. I'm actually down in sunny Florida. And you can't tell it's sunny because all of the curtains are closed at the moment, but it is very warm out. And we have actually a really exciting theme because we have two Americans living in England that are going to be presenting today. So there's American in England audio programming theme today.
That's pretty cool. I normally also live in England, although I'm not American, but right now I'm actually also not in England like yourself. I'm in Athens in Greece. So the weather is also pretty good here. So
as someone who's in London right now, I would say stay where you are. Yeah.
Right.
Yeah.
So yeah, Josh, that's cool. Florida, yeah.
Yeah, it's really nice out here. And yeah, I guess we should take a moment to give thanks to our sponsors, Focusrite Juice and Sonics. Thank you for sponsoring the Audio Programmer Meetup. And this is really cool. We have two great presenters for us today, very experienced, and they have some very exciting topics to talk to you about. So we have David Molnar and Jatin Chowdhury. And they're going to be talking to you about some really exciting things. And I think that we should just jump right in and go to the first presentation. What do you think, Teamer?
We totally should. Before we do that, let me just make one more comment. Everyone who's watching on the YouTube stream, please ask questions. We're going to ask them to the speakers, and you're hopefully going to get answers for those questions. But if and when you ask those questions on the YouTube chat, please prefix them with the word question in capitals. So it's easier for us to spot the questions in the chat because there's sometimes more chit chat going on there. So it just makes it a little bit easier for us to spot the actual questions to the speakers so we can ask them. With that being said, let me introduce your first speaker for tonight. I'm very excited to introduce David Molnar, who is the founder of Renegade Soundplay. And he's here to talk about HiScore, which is a sound generator that he has created. Take it away, David.
Thank you, Timur. Well, I'm David Molnar, founder of Renegade Soundplay, and I created a product called HiScore, which is a sound generator for 1980s video games. And one of the main goals I had for this product was I really wanted you to get that feeling you were immersed in 1980s video games. So everything from the sounds to the graphics. And I did it all in Contact. And I have to say, I really pushed Contact to the limits, and I'm going to get to talking about that. So let me show you HiScore. Let me bring up Contact. I'm going to share my screen and share my sound. Okay, so do you see Contact right now?
Yes.
Okay. And this is HiScore right here in Contact. And so HiScore, like I said, is a 1980s video game sound generator. So I actually created some sounds for it. I sampled some sounds. I'm going to talk about that. The idea was to be able to play sounds that you could play on something like a Nintendo NES, a Nintendo Game Boy, Commodore 64, an Atari 2600, an old Texas Instruments TI. I even actually sampled sounds off an old Texas Instruments TI 99-4A. That particular product has a very interesting speech synthesizer built in, so I took advantage of that. So, so just talking about HiScore, it works like a regular subtractive synth. So there is, I've got three oscillators I call wave generators, wave 1, wave 2, and wave 3. I've got a noise generator. There's an envelope generator for the volume, envelope generator for the pitch. I've got a pitch LFO, a volume LFO. I've got a separate envelope generator for the noise generator. And then the pitch and volume LFOs are actually assignable, and the pitch envelope generator, you can assign them to different places. In addition to the sound generator, I actually put it on a separate page because I ran out of space. I've got a filter, and it's a 2-pole or 4-pole filter that does low pass, high pass, band pass, and notch. And you can assign it to any one of the 3 wave generators or the noise. The pitch LFO and the volume LFO are assignable to the filter, but then you also have, the filter has its own envelope generator. In high score, I also included what I call the step arpeggiator, because one of the interesting things about old video games is they were so limited on the number of voices, so that if you wanted to play, say, a chord like a piano accompaniment, and then have a lead line, and then have a bass, and then have some drums, well, you didn't have that enough voices to do all that. Maybe you had 3 voices or 4 voices or something like that. So one of the things that you would get, you would, instead of playing that piano chord, you would have an arpeggiated chord. And let's just give you an example of that. Find a good one here. So let's see here. So instead of playing just the chord, it was arpeggiated. So I have the step arpeggiator, and you don't have to play fast arpeggios, you can play slow things on there too. And it's syncable to your host, which you'll need if you're using it in a DAW. I also added some effects. Let me just turn off that. So I have a note delay, because in old video games, you didn't have a real delay effect. You didn't have, there wasn't enough memory in there to do it. So instead, a lot of programmers just repeated notes at different volumes. So I created this note delay that just takes the note you play and repeats it. So let me just do something simple here. So let's see, if we come here and I turn on the note delay, that's just repeating the notes. And you can have up to 8 repeats. Another thing I put in high score was the speaker simulator. And you can come over here, it's turned off. But when I click on one of these 3 devices, it now sounds like it's coming out of this device. So this is an actual Sony studio monitor that I did an impulse response scan of. Also a ZX Spectrum, the speaker in the ZX Spectrum, and Game Boy. And that's the speaker simulator. So the nice thing about Contact is it's hugely customizable. So you're not only creating a skin, but you're actually writing code. And Native Instruments created something they call the KSP, the Contact Signal Processor, a scripting processor, excuse me. And let me see, I think I have that up here somewhere. Let me see if I can find that. So many windows open right now. Well, either way, they have there is a nice manual for that, which I seem to have lost. Here we go. So you can just go onto the Native Instruments website and download this. And it's pretty much, it's a very structured language, but it is not object-oriented. So it does have its limitations, but it's very usable. And so what kind of things you can do with their KSP language is basically assign all of the graphics to, all the graphics elements, assign them to various objects inside Contact. So if I click on this little wrench icon, we go under the hood, you can see here's the first oscillator square wave right there. And I come down here and you can see in Contact, you have all of these different effects. This is what's under the hood of Contact. So you can assign, using the Contact script processor, you can assign all of your controls that you have created, your graphics user interface, to any of these items inside contact. Right there. So yeah, so here I've created, this is my script right here, which is, how many lines of code is this now? 24,477 lines of code. They don't let you use multiple files, which is very unfortunate. So it makes for a big file. But you can do quite a bit with it. So let me see here. So yes, so high score works with, because it's in contact, it works with samples. And I recorded samples from the Commodore 64. I recorded samples from an Atari 2600. Some sounds I created myself. So like a simple square wave and some of the pulse waves, I actually just created those myself. Other sounds like the Commodore 64 sounds where there's like this real gritty tonality to them. I sampled those right off of the actual product. Spent a couple weeks sampling the Commodore 64. Let's see. Then one of the things I sampled, which I'd mentioned before, was the Texas Instruments TI-99 4A. And the thing about that was I wanted to sample some of the vowel sounds from the speech synthesizer. So if I just use the first oscillator here and I scroll down and I come to the speech sounds, let's find that. So like here, let me turn off that note delay. So that's just an ah, and then I did E. And I did the O. You know, I have to say that I did have quite a bit of feature creep as I was just doing this for myself at first. So I decided to go ahead and create a sound bank of words. 8, 13, 14, 13. So I have 2 sound banks of words, and I just so I just sampled a bunch of words off the speech synthesizer on the TI home computer. New insert send right destroy planet destroyer star moon white yellow orange green red black. So let's see. So I'm going to discuss here. I talked about the speaker simulator, and
one question is,
yeah.
What did you use to sample your recordings?
Oh, okay. So I actually, of all the things, I used Audacity. I recorded all my sounds into Audacity. And I know, cheap freebie app, but it worked well and did the job. Yeah.
Can you share anything more about the setup? Like, did you just mic the, like, how do you?
So like the Commodore 64, I took the audio out and ran that direct into my sound card. Things that I did mic. So when I did the speaker simulator and I recorded sweeps of things like the, in fact, I'm going to stop the share for a second. I'll show you. So let's see here. Okay, let's see. Can you see me now?
Yes.
Okay. So let's see. So I actually did a sweep through here, and I used Logic's sweep generator. And so I actually sweeped this, and it was sitting on my bench right in front of me, right behind where the computer screen is right now that I'm looking at you on.
This is amazing.
And I sweeped it, and first I played high score through it. And I just had the idea for the speaker simulator, and I used this, it's all boxed up. I had a little instrumentation microphone I bought for this. And I just set up some blankets around it to deaden the room a little bit. And I ran a sweep through it. And then in Logic, it'll turn that sweep into an impulse response. And then I just used the convolution reverb in Contact to create the speaker simulator. This, very short decay time, but it worked. I was actually amazed how well it worked and how I played Contact through the actual speaker in that monitor, in that Sony monitor, and I had an idea what it sounded like. And then I played it through the speaker simulator, and my speakers were positioned somewhat similar to where I had the monitor on my desk. And I was just amazed how it just sounded just like it. And it blew my mind. Then I did the ZX Spectrum, which I have right here. So I did the little speaker in the back. I don't know if you can see that. And I did the Game Boy right there. Now, the Sony monitor has an audio input, so I just ran the output into the input and recorded that. But to do these was a bit more complicated. I actually took them apart and I ran wires from the speaker to my mixing console. And that's how I did the sweep of these. And I just, had the microphone on a boom stand out in front, hit go and swept it. And then when I was finished, I unsoldered the wires and put this thing back together. And same here with the ZX Spectrum. Here is the very Commodore 64 that I sampled for all the Commodore sounds.
There's another question from Jas asking, have you ever thought about downsampling the 8-bit downsampling to 8-bit using simple 8-bit encode and decode? I'm not sure if I understand that question quite. Have you thought about downsampling to 8-bit using simple 8-bit encode and decode? I'm not sure. Jess, if you want to rephrase that.
I don't think I quite understand either. Yeah.
Yeah. One question that I was wondering is, because you come from a hardware engineering background, how did the knowledge of that contribute to your approach to making the product itself?
I've done a lot of hardware over the years for various music industry and audio companies. And I've also done a bit of embedded firmware. So I already knew C and C++. So I had that background, but I also had the music production background. So I wanted to start developing apps. But for me, I didn't know Juice, and it's still on my list of things to learn. So for me, the path of least resistance was to try and do it in Contact, because the basic framework was already there. It was already set up to go. Now, little did I know that I was going to need to do a lot of this scripting code. But for anybody who's interested in doing something for Contact, if you can program in C, you can learn the KSP coding. I mean, it's very simple like that. So, I mean, does my hardware background give me any extra experience? I mean, maybe because I knew how to hack into the speakers inside these things and wire them up or that kind of thing. I'm comfortable working on old vintage gear. I don't know if that quite answers your question. But
yeah, I think that helps.
Yeah,
that definitely helps answer it.
So I'm going to share my screen again. I want to show you something. Let's go back to my screen.
And there's a little bit of trivia, which is that a lot of people don't know, which is that Teamer used to work on the Contact team.
Yeah, that's true. That's true.
Yeah.
Yes, I worked on the Contact, the actual Contact app itself. Yeah.
Oh, very
cool.
cool.
Instruments. Yeah, that was quite a while ago. It was around 2014, 2015.
Sure. Yeah. No, that's great. Yeah.
Contact 5.5 was like the big release that I kind of did a lot of work on, but that was quite a long time ago.
When I originally started developing it, I was doing it for Contact 5, and I wanted to license the Contact player because not everybody has Contact. So I wanted to license the free Contact player from Native Instruments. So they said, well, you've got to do it for Contact 6. So that's when I moved up to Contact 6. Let's see here. So one of the things that I did inside here also is the custom wave generator. So let me just omit this. So we're in a consistent space here. And see all these Commodore 64 waves. And this is the custom wave generator. If you hit this edit button, it pops open this little See, look at that. I just went to move it. It doesn't move. It's a graphic, but it looks like a window. And the custom wave generator allows you to create your own very lo-fi waves. One of the things, like for instance, in the Nintendo NES and in the Game Boy, like in the NES, there's a triangle wave, but it's actually made out of 4-bit steps. So each step is one of 16 positions. So vertically in here, you can basically move one of 16 positions. Now I only did 16 steps horizontal because it's very resource hungry. Especially on my older MacBook Pro that I used when I developed this. Now on my newer MacBook Pro, I don't seem to have the problem with that, but not everybody has the fastest, latest machines. So basically, you can hear all these artifacts in the sound because of its very lo-fi nature. Now, I wish I had a scope hooked up that I could show you this. So how did I do this? Let me tell you how I did this. I basically created the narrow pulse wave that is 1/16 of the cycle. And when you hit a note, it is actually playing 16 simultaneous notes or voices, one for each step in the wave. And they're offset in time to account for each of the 16 steps. So that really is just a bunch of pulse waves being played in sequence to create the custom wave. And it does get to be a little CPU heavy. Like here, this one note press is taking 7% of my CPU right now. So originally I was going to do 32 steps, but it just was too much. So I did just 16. On the Game Boy, you can actually do a 4-bit by 32 step custom sound that you can create on there. But because of contact, I limited it down to 16. But I had a lot of fun making this. You know, I'm into old vintage video games from the 80s and 90s. And so I kind of went with that whole theme. I did all the graphics. I actually made all the graphics in GIMP, of all apps, the open source graphics editor.
Nice.
So, I mean, I don't have Photoshop, but I have an app called Pixelmator, but GIMP actually didn't do all this kind of crazy anti-aliasing that I couldn't turn off in my other app. So that was a nice thing about using GIMP. So.
Wow. Tima, did you understand Jas's question about
Yeah. So I think their point was that they were actually not talking about downsampling to 8-bit, but use like 8-bit bit depth, like using like an 8-bit encoding for the actual audio, and whether like that's something you considered. I think that's for.
Oh, I see.
Sorry, so they're writing, sorry, not downsample, but decrease bit depth using 8-bit encoding and decoding.
Right.
So that was the question. That was what the question was about.
Yeah, I see what you're saying. So if I was, you know, there's kind of two different things going on. You know, a lot of these old systems were just pulse waves. And so there's really no reason to do that. And you could play that in whatever bit depth you want. Then you know, the Commodore 64 has sawtooths and things like that, but that's done on a custom chip called the SID chip that most of you are familiar with. So I did not do any bit reduction on that, no.
I guess that would be like a bit crusher, right? That's quite a different effect from like
that is
kind of what you're going for in here.
Yeah. Yeah.
Can you talk?
You know, if I was playing, if it was like an Amiga where you're playing back sounds through the Paula chip on the Amiga, that is a true 8-bit kind of sample playback system. But here, no, I'm not doing anything like that. No. The custom waves actually turn out to be 4-bit.
I was wondering if you could talk a little bit just about so a lot of people want to start up their own plugin companies, want to sell their own products, and I was wondering if you could just tell them a little bit about your marketing marketing ploy and your website, and just a little bit about the brand and that side of things.
Sure. Sure. So I mean, I've done it all. So I mean, I'm in addition to like doing all the coding and sound design and all the sampling, create all the presets, all the graphics for the product. I mean, I handle the website. And so for the website, I created a Shopify website. But if you wanted to market your own products, if you want to sell them yourself, I created a business entity here in the UK. So I created a private limited company in the UK that is Renegade Soundplay. And so I did that. And so then I opened up, business banking. I mean, I did the whole, it's a whole business that I'm running basically for this. And I've got more products in the works, which hopefully will be coming up in the new year, actually. Yeah. But yeah, oh yeah, I mean, it's as far as marketing goes, I did an interesting marketing exercise in the beginning. So when I started the business, I created, I did a Kickstarter, and I created a Kickstarter to mostly get the word out about HiScore, because nobody's heard of the product, let alone my little company. So I actually ran a Kickstarter for a month and had various rewards, and that kind of spread the word about HiScore, and paid for the licensing fee for Native Instruments, which was nice. Oh, yeah, so I worked with Native Instruments and licensed the Contact Player. They're very nice people, very easy to work with. What else? Josh, any more questions in that vein? Anything specific you want me to talk about? As far as marketing, I did a lot of Facebook ads, both during the Kickstarter campaign and afterwards. I ran Kickstarter ads for a while. Excuse me, Facebook ads for a while. I've done social media stuff. It all comes down to like, I'm just one person and there's only so many hours in the day these days. So if you have other people you can work with to help with some of this, I highly recommend it. Yeah.
And what
Can I
about?
ask you, sorry.
Yeah, go ahead, Timur, please.
Can I ask you a question? Is this something that you like live off now, or is it just like a little side project and you have like a month where you're doing something else?
It's provided a good chunk of income for a while. I got to get some more products out, but eventually I'd like to just live off of this. Eventually, yeah.
I was going to ask. There's a question actually from Sono Lumi. How did you generate the consonants in speech synthesis? Is there a standard method? Yeah, go ahead.
Yeah. So like I sampled all those sounds. I sampled them off of this 1981 TI 99 4A computer. I don't know if you can see this section on the side is the speech synthesizer. I don't know if you can see that right there.
Yes, you can see it.
So all the sounds were actually sampled off here. So and like I said before, originally I was just going for the vowel sounds because they're very musical, and I was just going for that. And as I was going along, and I was just typing in words and having the TI computer say them back to me, I said, well, wouldn't it be fun just to put a bank of speech sounds in there, and people can just include them in their productions, and if they want like some classic phrases from old video games, they can just hit different keys to come up with some phrases. So I just put individual words, and that's how I did it. So there wasn't any kind of, I didn't generate those sounds per se, other than just the TI home computer did it. And I just kind of went into the basic programming language on the TI home computer and typed in a few lines of code and just played back the text for me. Yeah. And then I just sampled that into Audacity and sliced and diced it.
Yeah. I know Jatin is really happy about this because he loves analog modeling and analog gear. So this is right up his street for sure.
Oh, you may want to look up. I'm sure there's plenty of articles on how they made the old speech synthesis, like Texas Instruments did it. I know it uses linear predictive coding. Beyond that, I can't speak much to it. there's a whole there's a special cartridge for the computer that was of all things the terminal emulator cartridge, so you can turn your computer into a terminal. But when you added that cartridge in, you could jack into the speech synthesizer in the regular BASIC, the built-in BASIC. Very weird. This computer also, in hindsight, I didn't know it as a kid when I was using this computer, but it has a really weird system architecture. It has a 16-bit CPU that is bust 8 bits out to all the peripherals, so it's not really being taken advantage of. And when all the registers reside in RAM, actually, so that they're not very fast. But it was cool for the time. But yeah, look up Texas Instruments speech, and you can learn all about it. Yeah, I think it's the same chip they used in the Texas Instruments Speak and Spell, actually.
Amazing. Do we have any other questions or comments from the audience before we finish up? I'll give a couple seconds for the delay of the video to catch up before
I see one that's maybe interesting. CGO435 asks, is there any legal stuff involved in sampling sounds from hardware and selling them?
The sounds that I sampled, I would say no. They're not actual. You really run into legal problems if you're sampling from products that use samples, because those samples are covered legally like a recording that you've done. Whereas I'm just sampling sounds made by raw sound generators.
So
Even the speech is actually generated. Yeah.
So is it basically like you buy a guitar in a shop and then you sample that guitar that you bought? Yeah. Is it basically like that?
Yeah, like that, or you have a piano, or you have a violin, and you record samples off of that. Yeah.
Plus, I think another key element of that, not being a lawyer or anything, is that you're not looking to market it as that product in software form as well. So if you...
I am not. I seem to recall, I don't know how many years ago now, somebody went to the trouble of sampling a bunch of sounds from a Roland D50 and marketed it as a kind of sample product that, a VST that plays sounds of the D50, and Roland went after them for that.
Yeah.
Because the D50 uses sampled tags. So, or for instance, you could get away with sampling in 808, but you can't get away with sampling in 909, I believe. Because in 909, I think it samples.
Really? A lot of lawsuits out there waiting to win. A lot of lawsuits waiting. Yeah.
Like you wouldn't want to sample a Korg M1 because that's all samples. So the samples are covered by copyright law for recordings. But you can sample a vintage synth where you just have an analog oscillator, for instance, generating a tone.
Okay. Looks like we're out of questions. Anything else from anybody before we wrap it up?
I think we can wrap up. Yeah, but that was amazing. Thank you so much.
Yes.
Thank you.
It was so much fun.
Yeah, that was a lot of fun. And if you're wondering how to give a talk, and if you have a talk idea and happen to be watching the presentation, we're always looking for more people to submit a presentation. And you can find out how to submit your presentation. And you don't need to be a 20-year vet in the industry in order to make a presentation and share your ideas. We welcome people that are also speaking for the first time as well. And you can find that on theaudioprogrammer.com/submit. And then we also have the Audio Programmer community. We have nearly 7,000 members now in our Discord community, where we share ideas about all types of things, about DSP, about becoming a better software developer, and about everything else. And you can join us there on theaudioprogrammer.com/community. And with that, I think we can go into our next talk. So, Timur, would you like to introduce our next speaker?
Of course. So our next speaker is Jatin Chowdhury, who is a plugin developer at Chowdhury DSP. And he's here to talk about analog modeling with wave digital filters in C++. Definitely want to hear more about that. So please take it away.
Thanks, Timur. Yeah, hi, everyone. So as Timur mentioned, I'll be talking about wave digital filters. And I put together some slides here, which I'll show on my screen here. And then I I have them online here. I think I don't know if it's possible to put like a link to these slides in the chat or something. That would be nice.
Yes, we will.
Cool, thanks. But yeah, so I guess just a little bit more about me. So I'm originally from Denver, and then I studied at Stanford for a little while, and now I just develop plugins, mostly for myself and whatever I find interesting or whatever I want for my own mixing projects or things like that is what I usually try to work on. But yeah, so I wanted to talk about wave digital filters because I think they're a really interesting sort of meeting of being a really interesting signal processing concept and being something that is very challenging to actually write the code for and implement. And when I try to talk about this with like people who are very theoretical signal processing people, they don't always care about the implementation details so much. And if I try to talk to people who only know programming, they don't really understand some of the signal processing behind it that leads to certain parts of the implementation. So I thought this meetup would be a great place to talk about this stuff because I think it's a nice cross-section of people who understand both sides of it and who care about both sides of it. So I thought that would be a cool way to talk about this. And I want to give a big thanks to Julius, Kurt, and JJ for kind of teaching me and walking me through all of this wave digital filter stuff, and then for Paul and Dayal, who both gave me some really nice C++ tips, which I'll show you guys in a few minutes here.
Jatin,
Yes.
just to interrupt very briefly, your voice has gone very glitchy. I'm not quite sure why.
Oh no. Okay.
Yeah,
And there's a lot of background noise. You seem to have like some kind of noise gate going on. So whenever you stop talking, it's becoming silent. But when you start talking, there's just like a weird glitchy noise, which makes it a bit difficult to understand. I'm not sure if it's just me or
it seemed to happen when you started sharing your screen.
Oh, weird. Okay. Yeah, I tried changing my.
Oh no, it's still happening now.
Still happening. Oh man.
Yeah, I hear it too. Yeah.
Can you check which like audio interface you're using or something?
Adjust my settings here.
Apologies, like we did do a sound check before the show, but apparently we missed something there.
Yeah, all this lo-fi talk.
It is lo-fi.
Yeah.
Yeah.
It actually sounds pretty cool. So if we can wrap that up into a DSP, that would be really awesome.
Yeah. How's this? I tried changing things again.
Can you say something?
Testing. How's that? Hello.
Seems better.
Okay. I'll try sharing the screen again and hopefully that won't ruin it. Okay. Still talking. It sounds okay?
Yep. Sounds like we're
awesome.
Here. Yeah.
Cool. Okay. Well, yeah. Thanks for catching me on that. Yeah. So this is just a quick outline of what I was going to talk about. I'll give a really quick introduction to wave digital filters and then talk through a couple different implementation strategies. And then I'll show the library that I'm currently using and some stuff that I'm planning to do with it moving forward. So yeah, wave digital filters is a big topic. Probably, I don't know, be worth like a few hours of talking. So I'm just going to keep it very simple and just try to capture the smallest amount of information you need to understand the implementation that I'll talk about next. So wave digital filters, or WDFs for short, are a way that you can approach modeling analog circuits. And the way that it's different from most other ways that you can do this is that it allows each circuit element to be discretized independently from the others, which allows for a sort of modular way of modeling circuits where you can swap out components or change things around very quickly and easily without having to do a lot of extra work. And my personal feeling about using wave digital filters is that I like that when you use WDFs, if you're modeling a simple circuit, then you wind up with a simple model. Whereas with many other approaches, even if you're using a very simple circuit, there's a lot of complexity in just setting up the simple circuit model. So that's why I like WDFs personally. As an example, this is a very simple low-pass filter circuit. So it's just a resistor and a capacitor, and then some input voltage, which is this VN voltage source here. And then the output is just the voltage across this capacitor. So you can build the circuit on a breadboard or something like that with just a couple of components, and it's pretty easy to fiddle around with. So let's say that WDFs did not exist. The way you might try to model this type of circuit is with this method called nodal analysis. And the way that that works is you do this thing called a Laplace transform, and that puts everything in terms of this variable S. And then you can construct this transfer function, which is the output voltage over the input voltage. It depends on the resistance and the capacitance of your components. And they call the transfer function H, just for whatever reason. And then you have to discretize the analog transfer function. And there's a bunch of different ways you could do that. But in the end, you'll wind up with this discretized transfer function here. So you've got these three, what they call filter coefficients, which are B0, B1, and A1. And then you could use that to implement a digital filter that models this circuit. So that's how you could do this with nodal analysis. But one thing that I find frustrating is that whenever you change a component value, like if you want a potentiometer or something like that to be able to change the cutoff frequency of your filter, then you need to redo the discretization step. So as soon as this R value changes or the C value changes, you need to redo the discretization to compute these filter coefficients here in the discretized transfer function. And even worse than that, if you want to swap out your components or something like that, like let's say we want to swap out our capacitor for an inductor, then we need to rederive the whole thing. None of this stuff can be reused. You would have to rederive this analog transfer function and then go through all the math again from there. So what if we could make nodal analysis a little bit more modular? And one way you could try to do this is to discretize each component separately. So you come up with a discretized resistor and a discretized capacitor, and then you just plug them together in whatever configuration. And unfortunately, this doesn't work because you end up with these things called delay-free loops. So this is a slide that I borrowed from one of Kurt Warner's presentations, and he goes through the math in a little bit more detail. But when you try to discretize a circuit like this using just sort of the nodal analysis approach, you end up with a structure that looks like this, where you've got a delay-free loop here. And what that means is that if you were to try to write code for something like this, it's not computable, at least not with the sort of standard, straightforward signal processing tools that we have. There are some ways to resolve delay-free loops, but we typically try to use those only when we have a more complicated circuit where that's kind of our only resort or our only option. So the way that Wave Digital Filters gets around this issue of delay-free loops is using these things called wave variables. So we do a change of variables. So instead of looking at our circuit in terms of voltage and current and things like that, we instead examine everything in these wave variables. So this is the definition of the wave variables here. And the way that you can think about this is kind of like a different way of imagining the way that data gets in and out of our circuit components. So in the traditional model, you have some circuit component with an impedance R0, and you have some voltage that's across the component and some current that's going through it. In the wave domain, you still have that impedance R0, but now we have an incident wave going into that element and a reflected wave B coming back out. So that's a single wave digital filter. And when you kind of combine these wave digital filters, you get what's called a WDF tree. And so that's what we're looking at here. You've got some circuit component here, some other circuit component there, and those are connected in series with this root component here. And I'll talk more about what the root is in a second. One thing that's a little bit sort of tricky to grasp when you're looking at a diagram like this is that the incident and reflected waves are kind of flipped between the components. So Here, A is the incident wave and B is the reflected wave from the perspective of this component. But for example, here, if we're just looking at this connection, this arrow is the reflected wave from the series node. That's the incident wave to this R1 node there. So that's something to keep in mind when you're reading these diagrams. So the rules for wave digital filters are fairly straightforward to get started with. So you have these things called ports, and each port has three variables: an incident wave, a reflected wave, and a port impedance. So that's what we're looking at here. This is one port, basically. And there are some circuit elements or some nodes that we call leaf nodes. And these are one port nodes. So a resistor, a capacitor, an inductor, these are all just one port. And then you have what's called adapter nodes, which are 2 ports, 3 ports, maybe more. And so like a series adapter would be 3 ports, like the one that we're looking at here. So the reason why they're called adapters is because they adapt to the port impedances of the attached elements. And so what you end up with is one port that is considered a reflection-free port. And we'll see what that is in a second, but the purpose of the reflection-free port is to allow us to make this circuit model more modular and to not have delay-free loops. And then finally, there are these special unadaptable nodes, which need to be at the root of the tree. And since your circuit can only have one root, or since your tree can only have one root, you can only have one unadaptable node in your tree. So the way that the sort of adapting process works is that if you have your series adapter here, you can think of the series adapter as having sort of one parent, which is the root, and 2 children, which are R1 and R2. And then what you can do is derive the port impedance R0 that's facing the root node such that this port becomes reflection free. And so what that means is that the root node doesn't need to know anything about what is happening with R1 and R2. It only needs to know this port impedance that it's facing, R0, to do everything it needs to do. And this kind of restricted flow of information is what allows this modularity to work and to avoid having any delay-free loops. And so what's nice about this is that if we change this resistor to a capacitor or something like that, then all we need to do is recompute R0, and everything in our circuit will work just like it did before. And then finally, we can set our root node to an ideal voltage source. And now we've got our RC low pass filter back. So just like before, we have a resistor, a capacitor, and a voltage source all in series with each other. Sorry there. So now that we have our wave digital filter tree set up, we need to figure out a way to actually do the computation that gets signal in and out of this structure. And so the way that we do that is by going through these steps here. So first we need to set our parameters basically. So if we have potentiometers or any other sort of variable components, we need to set those component values. Then we need to basically give our circuit some input. So if we have a voltage source, we need to tell it, hey, here's the voltage right now. And then we can actually run signal through the tree. So the way that works is we propagate our reflected waves from the leaf nodes to the root. We do whatever computation is needed at the root, and then we propagate waves back up to the leaf nodes. And then finally, we can figure out what our voltage is or current is to get the output of the circuit. So to just go through that in a little bit more of a visual way, the step of propagating the reflected waves from the leaf nodes to the root looks something like this. So we have our leaf node R1, and that has a reflected wave going into the series adapter here. Same thing with C2, it has a reflected wave going into the series adapter there. And then that has a reflected wave going down into the root node there. Then looking at the voltage source here, there's a reflected wave going here, such as an incident wave going in, and then we do some computation here to get the reflected wave back out, going back into the series node. And then the series adapter will take that incident wave and compute the incident waves going back into the R1 and C2 nodes. And then finally, we can just look at what the voltage over C2 is at that point, and that's the output of our circuit. So you might be looking at that and say, well, hey, that seems a bit more complicated than the nodal analysis stuff that we were doing before. And in a sense it is, at least the first time that you do it. But what's nice about it is that all of the work that we just did to try to understand this, this wave digital filter structure can be reused for the next circuit that we want to model. So for example, if you look at a diode clipper, now we've got a voltage source, resistor, capacitor, and then a pair of diodes, and then the voltage across those being the output of the circuit. We can use pretty much the exact same structure in a wave digital filter to compute this circuit. So we can combine our resistor and our voltage source into what's called a resistive voltage source, and then have that in parallel with the capacitor and our diode pair. And it's pretty much the exact same computation, just with slightly different things happening in each node. So I've given a very brief description of how wave digital filters work, but if you're curious about it, I've got a bunch more papers here that are really cool. So going back to 1986, Alfred Fedweis has a really nice sort of overview of the origins of wave digital filters. And then there's a bunch more sort of more audio related papers here. So Julia Smith and Kurt Warner have done some really great work on wave digital filters. In particular, Kurt Warner's PhD dissertation, I think is a must read if you're really looking to understand wave digital filters for to be used for modeling audio circuits. Cool. I'm gonna drink some water real quick here. So yeah, now we want to actually implement this, all of this interesting signal processing stuff in some C++ code. And so when I first started working on this, maybe probably like 2 years ago now, the first thing that jumped out at me was that it seemed to very naturally fit into sort of an object-oriented polymorphic way of looking at things. So when I started working on this, I set up a base class, something like this, where you have for each wave digital filter sort of port, you have a reflected wave, an incident wave, and a port impedance. And then you have methods for sort of computing what happens when there's an incident wave going into that port, or a reflected wave going out, or when you need to calculate the impedance because some impedance that's facing that port has changed. And so you can set up a resistor and a capacitor and an inductor, these types of simple elements just as child classes of the WDF base class. And then for adapters, you can set up a pretty simple class, something like this, where you have pointers to your child nodes, and then you store those in your class. And then, for example, you could make a series adapter that's just a child class of your 3-port. And then all you need to do there is call an incident and reflected method. And the important thing to see here is that when you call incident on your series adapter, that will in turn call the incident method of the child ports. So that makes it really easy to actually run the processing later on, which we'll see in a second. And then finally, you need to be able to probe any of your nodes to get the voltage of the current at a given time. So if we were to try to actually process some signal with this very simple polymorphic implementation, it would look something like this. You create a capacitor, resistor, your series junction that connects those capacitor and resistor, and then you create your root node that knows that the voltage source, or sorry, that knows that the series adapter is the facing, the port that's facing it. And if you were to process a sample of audio or a sample of some digital signal with this wave digital filter tree, all you have to do is set the input voltage and then do this little thing here. So what you're doing is you're calling reflected on the series adapter, which will in turn call reflected on the resistor and capacitor. That will sort of get all the reflected waves, bring them down to the root, and then you call incident on your root node. And then you sort of flip the operation where you call reflected on your root node, and that becomes the incident way of going into the series adapter. So that's basically the 3 diagrams that I had earlier that showed kind of the signal flow through the wave digital filter tree. And then finally, you use this voltage method to get the voltage over your capacitor. So this is what I had been using for some time. And then maybe 6 months ago, Paul Walker from the Surge Synth team showed me that there's kind of some problems with doing things this way. And I'll try to explain what those problems are here. The main problem is the way that the compiler sees this sort of structure. And I have a little example here in the compiler explorer. Okay. All these Zoom windows are blocking my screen here. Okay. Cool. Yeah. So this is that example that I was just showing you guys in Compiler Explorer. And when we look at the process sample method, even though we're compiling with all of our full optimization flags, you can see all of these call functions showing up here. And so what's happening there is that the compiler is not able to inline almost anything from this wave digital filter tree just because everything is happening polymorphically. So when, where's our series adapter? So when this port 1 incident call happens, the compiler doesn't know at compile time what type port 1 is. It just knows that it's some wave digital filter element. And so this call operation that keeps happening there ends up taking a fair amount of time when you're actually trying to run the wave digital filter tree in your plugin or in your synth or whatever. And so what's happening is the compiler, it has to do what's called a vtable lookup to try to see what, or to try to find the actual function that it needs to call to do that operation. So since this implementation is using polymorphism, every time we call that incident function or that reflected function, the computer has to look up where that function is and then call the function and then return. And all of that takes a little bit of time. So what I try to do in general is to not have to do a vtable lookup per sample because I think that's kind of slow. It won't, max out your CPU or anything, but those types of calls add up when you have, 10 or 20 instances of a plugin running in your DAW. And so this is even worse for wave digital filters because for every node that's not the root node, you would need 2 vtable lookups per node per sample. So for our very simple RC low pass implementation here that we were looking at, you need to do 6 vtable lookups every sample, which is not really where you want to not really where you want to be when you're trying to run this thing in real time. So trying to think about that problem led me to thinking about trying to implement wave digital filters with templates. And this is where Eyal helped me a bunch, and a bunch of what I'm going to show you here is stuff that I came up with while working with him. So instead of having a base class, I made a little macro. Kind of grade some things out here, but I made a little macro that sort of creates these member variables for me. So what was a member variable in the polymorphic implementation is just a macro definition in the template version. And so for a simple node like resistor, almost everything would be the same, but then you would use your macro to create your variables for you. And then the adapters are really where sort of the magic happens. So instead of taking pointers to our child elements, we actually have to tell the compiler through templates what types we're going to be using for our child elements. So we say, okay, there's going to be some type connected to port 1. So we'll call it port 1 type, and then some type connected to port 2, and that'll be port 2 type. And so now when we're calling incident here, the compiler knows exactly what we're calling because they know exactly what port 1 type is. And then for the probe methods, it's just a tiny bit of extra work to give it the template type. So when you need to get your voltage over a node, you can do it like that. And so for actually running the Wave Digital Filter tree, it's almost the same. The only difference is that when you're creating your nodes of your tree, whenever you have sort of a dependent type like this, you need to give the type these template arguments here. And this is a little bit frustrating for me because if you're creating these things outside of a class, then you can use auto here to determine those types for you. But if you want these types to be member variables, then you can't do that. They have to be declared kind of like this. And so if you look at what we get from Compiler Explorer when we actually template things, this was the old one. This is the new one. When we have everything templated, if we look at the process sample method now, there are no call instructions. And what that means is that the compiler is actually seeing through this entire method. So it sees through everything that we're doing in these methods, and it's just writing out the instructions for what's happening internally. And so what that leads to when we're actually running this is that it allows the compiler to not only inline the functions, but then do further optimizations. So if the compiler sees that the resistor is only doing a multiply or something like that, or it's multiplying by some constant, maybe it will try to do some optimization to sort of, fuse that into a multiply add or something like that. And just from measuring this on my own computer, I found that the templated implementation is usually about 2 to 4 times more performant. The sort of negative sides of the template implementation is that the circuit topology is fixed at runtime. So if you want to swap out a capacitor for an inductor later on, you can't really do that, or it's not easy to do that with the templated implementation, whereas it is pretty easy with the polymorphic version. The other problem is that the actual, like if you actually look at the code for how it's implemented, it is a little more complicated, but I don't think it's too bad. But I have, seen it, I know that it does seem scary seeing templated code for the first time, especially if you're kind of new to C++. So I get that can be difficult. So yeah, finally, I wanted to talk a little bit about the Wave Digital Filter library that I've been working on for the last, I don't know, couple of years now. And then this version of the library is maybe a few months old, and I've been working on it the last few days here as well. So this is the library that I've been working on, and it's actually on GitHub, and you can click this if you're looking at the slides and find the link to it. And the way that I have it working right now is that it's part of a juice module that I've been working on. So you can include it in your project as a juice module if you're using juice, but it's also set up so that you can just include a few headers. It's all header only. And so if you're using a project that's outside of juice, it's pretty easy to use that way as well. For licensing, right now my juice module is GPL. And so the Wave Digital Filter parts are also GPL. But I've been thinking about maybe trying to split off the Wave Digital Filter library into more of its own thing. And then, I don't know, I might consider using a more sort of relaxed license like a BSD or something like that. But we'll see what happens there. And yeah, so the library has both a template API for doing Wave Digital Filters at compile time, and also a polymorphic API. So if you do want to do the kind of runtime switching of changing your circuit topology on the fly, then you can do that as well. And I've got unit tests and documentation for it as well, which I'm pretty happy with. There's also a few sort of more extended things that we haven't really talked about today. So there's some diodes and other nonlinear elements that are implemented. There's these special adapters called RTEC adapters that I've been working on recently. You can also use the library with SIMD data types. So if you have like a synth voice that's being done as a circuit model, you could use a SIMD to get, I don't know, 4 or 8 of those voices all for the same price, basically, or the same CPU cost. And then you can also extend it to include your own custom circuit elements. Like if you have your own special diode implementation that you like, you can extend the library to use your own stuff too. For performance, this is kind of related to the 2 to 4 times improvement that I was talking about before. I'd set up a little benchmark with my friend Dirk, who had written the Faust Wave Digital Filter Library. And so we were just trying to compare performance between the different ways of implementing wave digital filters. So yeah, for some reason on this feed-forward network, the Faust library does really well. Although it takes like 5 minutes to compile the Faust code for that. But it does do a really good job. But other than that one, the templated library is usually pretty fast. I've also got a little examples repository. So I've got a bunch of example circuits that I've set up here. So there's some very simple things like a voltage divider, a current divider. There's a diode clipper. There's a Baxendale equalizer that I've been working on the past couple days. There's a couple of circuits from the TA08 kick drum circuit. And then there's a little wave digital filter prototype, which actually I'll try to show you guys here. I have to switch over to my other computer. Maybe I can show you guys this. Cool. Can you all see that?
Yes, we can.
Cool. And then let's see, turn on audio. Oh, and I need to unmute myself too. How do I do that? Okay. So yeah, this is yeah, so that's a little guitar loop. And then this is the low pass filter circuit that we were looking at. You can just do simple low pass filter things. There's a diode clipper. So you can do distortion pretty easily. And then the prototyper is something that I've been working on, or that I was working on like a year ago. And then recently I tried to revive it a little bit. But the way that this works is you can actually sort of build your wave digital filter tree here. So this is our root node, and maybe we want that to be a diode pair. And then let's try to build a simple diode clipper here. So we can do a capacitor and a voltage source. And then we set the voltage source to be our input, and the capacitor will be what we're probing to get our output. And then maybe we want our resistor to be like 1,000 ohms or something. Yeah, and then you could make your capacitor a different value as well. I don't know, -9. And then for the diodes, you can change some of the diode constants. And then you can actually change the number of diodes too, because the diode model that I use has some parameters for that. So we could even do like half a diode or something, which is kind of fun. But yeah, so that's kind of how you can use the little prototyping tool there if you're curious about that stuff. And then, yeah, I'll switch back to my slides here. But yeah, so these are kind of the next steps that I'm planning to do for my wave digital filter library. Right now, I'm working on improving support for R-type adapters. I have some ideas for maybe trying to improve the performance of the runtime API. I had an idea of maybe using std variant or something like that to be able to swap out components at runtime with less of a performance hit. And then there's a few other sort of fancier things I want to work on down the line. But yeah, so thanks all for listening, and happy to take questions or anything like that.
Wow, pretty intriguing presentation. And you were still having some glitching that was happening through the talk, but I was going to see if maybe you'd be interested in just recording it again in your own time, and then what we could do is we could do a fresh upload for you, make sure that people understand you clearly. But I think
Sure, yeah.
I think the main thing was that people really got an idea of what you were presenting, and they could hear you clearly, and people are blown away. We do have a few questions, so I'll start with the last question first. From operator, do you
Sorry,
use?
should we stop sharing the screen maybe so that
Yes.
you're visible again?
There we go.
Yeah. So we'll start with the last question first, which is, do you use Spice software to emulate digitally at all?
I do use Spice, but not so much for digital emulation. Usually the way that I use Spice is I use that to kind of verify my emulation. So especially for nonlinear things, it can be hard to know if your model is right, especially if you don't have the circuit right in front of you, which I usually don't because I don't have a lot of gear with me. So usually what I'll do is if I'm looking at a circuit, I'll make a Spice model, I'll generate some data, or I'll put some data through it and see what it looks like on the output, and then I'll make my wave digital filter model. Or you could use any other modeling paradigm, and then afterwards compare that back to the Spice data. And if your model's correct, then usually they're about the same.
Great. And yeah, go ahead.
Yeah, I do have a couple of questions, so I can't help it, but like put my C++ committee hat on. I apologize. You had this macro in there where were you like declaring like variables or something in there?
Mm-hmm.
So did you consider doing like a mix-in where you like inherit from like a class, but don't do it like, you don't have like polymorphisms, or nothing is virtual, but you just put those things into a struct and just inherit from that struct?
Yeah, I had thought about that. And that's probably a good idea to do in the future. Yeah,
it's just maybe a bit cleaner than
structure
having
those
a macro.
variables. Yeah,
you don't have to have that line in there.
Yeah, that's a good idea. I should do that.
Great. And Andrea Ongora has a compliment for you. Says, nice job. Loved your paper on nonlinearity modeling. Keep up the good work.
Oh, thanks.
And we have a question from Josh, who says, do you use any other templates other than Omega, which approximates Lambert W by Stefano for diode modeling? It's very efficient. For a long time, I was just using lookup tables.
Yeah, so for diode modeling, there's a kind of tricky function that you have to implement in some way, which is there's like the Lambert W function and the right omega function, and they're like related in some way. I forget exactly. But yeah, Stefano D'Angelo has a really great implementation really for any audio applications where he's using some tricky like bit manipulations for doing like 2 to the x and log 2 of x and things like that, which can really speed up your code a lot, aside from doing lookup tables and things like that. Because yeah, if you were to actually compute like the Lambert W function at runtime, it can be pretty heavy.
Great. And Josh Rose asks, while modifying WDFs is easier than re-deriving in Laplace domain differential equations for changes to the circuit, how does implementation compare in terms of computational expense in your experience? Did you address that in the talk?
Not really. I was more talking about comparing like different types of wave digital filter implementations. Yeah, I've done some like comparisons on that sort of thing. I found that for like super simple circuits, like if it's just like a second order filter or something like that, usually the IIR filter implementation will be faster by like, a little bit compared to the templated implementation. But for more complicated circuits, like especially if you have a nonlinearity or something like the diode clipper circuit, I found that the wave digital filter will usually be faster, but obviously that depends on what sort of approximations you're doing and what implementation, like how you have each method implemented.
Great. And Ed GJJ asks, if I'm wrong, it looks like we can avoid writing decal type on series specialization since C++17 due to CTAD. I'm not sure.
Yeah,
Not sure.
CTAD, class template argument deduction. If you declare a variable, you don't have to type out the template arguments. You can just write std vector v equals something. You don't have to write std vector of int anymore. But I'm not sure if this actually helps you. I don't remember what the actual code example was.
Yeah, it's
I don't think that actually helps you exactly in that case.
Oh, okay. Yeah, I found that for some reason, like there seems to be a big difference between declaring a variable like anywhere and declaring a variable as a class member.
Yes, there is a good
I don't
reason
fully
for that.
understand.
Yes,
Okay.
it's complicated, but it has to be that way. Like the simplest version of this would be that you need to know exactly what the layout of a class is. Like, you know, when you parse it, you need to know like these are the member variables. They have like that size, and if you like, you don't want to basically evaluate other stuff in order to find out what the types of the member variables are, because it makes it more difficult for the compiler to figure out what the layout of the class is, like how big the class is and what the layout of that is. So you run into all kinds of problems if you start doing that. So that's why compilers don't do that, and that's why if you declare a member variable, you have to spell out the type, because that just otherwise it would just be very difficult to implement in a compiler.
That makes sense. Yeah, thanks for enlightening that.
Great. And Ivan from Tita Productions says, great talk, Jatin. Are you planning to release this prototyper at some point? Sorry if I missed this. Good to see you again after ADC.
Yeah. I don't have any immediate plans for that. It seems, at least from where it's at right now, it seems like you kind of need to understand a little bit more of the Wave Digital Filters background to be able to really use it. But I was actually hoping, I was going to mention this in the talk, but then I forgot about it. If anyone out there wants to kind of work on that project or contribute to it, or take ownership of it in some way, I would be more than happy to help people get started with that. I think, I don't know, so that someone out there I'm sure has some idea of how to make it really cool, and I would love to see someone kind of do that. I haven't really figured it out in my head, like how to make that something that end users can really use, aside from like DSP engineers and stuff like that. But yeah, I would love it if someone has some ideas for where to take that.
Awesome. And where can people get in touch with you if they want to get in touch with you to talk about that project?
Yeah, well, I'm on the Audio Programmer Discord. I think my username, my first name, and then I think I had this on my last slide there, but I have my email and then my GitHub as well. So yeah, probably for that specific thing, that the GitHub page for that project is probably the easiest way to find it. Put a link here somewhere.
Okay. And we have some more questions. So George asks, do you think WDF composes better or worse compared to state space methods?
Yeah, it's I think it depends on the circuit. Yeah, so state space methods are usually kind of built off of that nodal analysis approach, or the way that I've done them is usually built off of that. And so it really depends on the circuit. I think some circuits end up working out really nicely in state space form, but it can be a bit nastier for other circuits. Whereas with Wave Digital Filters, aside from like the more complicated circuits, which need a bit more work, and I don't really want to talk about those today. For those kinds of things, I think it's about equivalent complexity between state space and Wave Digital Filters. But for simpler circuits, some things work really nicely in state space and some things are a bit harder. Whereas Wave Digital Filters, they're all more or less the same, which is kind of nice.
Nice. And Z Tony HD asks, I was wondering if you've read David T. Ye's outline of his K-method way of simulating diode clippers. If you have any experience with this, anything to say about its implementation or thoughts about it?
Yeah. The K method is really cool. Actually, David used to be my boss pretty recently. He's a great guy, but yeah, the K method is nice. I don't use his method for diodes very often. I prefer, or personally, I prefer one of the other methods that came a little bit after that. I think it was, I'm forgetting the name of the guy. Yeah, I'm forgetting the name, but there's a paper that was a little bit, I want to say 2014, so a few years after some of David Ye's papers that had a pretty good approach. And then Kurt Warner kind of built on that for his wave digital filter diode model.
If I need somebody to write me a filter, I know who I'm calling. A question from Cameron. Can we expect any upcoming products from Chowdhury DSP? Or are you currently working anywhere else or just self-employed?
Yeah. Well, I guess for the second thing, so I'm still making open source plugins and stuff like that, which is a lot of fun. And then I've also been working as a freelance plugin developer a little bit for the past few months. And then, yeah, for Chowdhury DSP, I've been working on an update to my Chow Matrix plugin, which will have iOS support coming pretty soon. Well, once I fix all the problems with it. And then I'm working on a new guitar pedal kind of thing. I've been learning guitar recently, so I wanted to make a plugin that I could kind of make along with while I was learning guitar. So that's been a lot of fun.
Yeah.
Also, the Surge synthesizer team is getting very close to their new Surge XT release. So I'm really excited for that. It's probably going to happen maybe February of next year. So yeah, that's been a lot of work, and the folks over there have been doing a great job. So really excited for that too.
Yes, big shout out to Paul and the Surge team doing big things over there.
Yeah.
Bacon Paul. Yes. And it looks like there's one. Let's see. No, I think we're good there. Okay. Great. I will give a couple more seconds for people to ask any more questions. But in the meantime, Jatin, I didn't understand a thing of what you presented there. It's been a while since I've had any of that I've seen a talk that I didn't remotely understand any of it. But wow, really impressive, really great sound, and thank you so much for joining us.
Yeah, thanks for having me.
Yes.
Thank you, Jatin. I really enjoyed that. Thank you so much.
Yeah, thank you.
Oh, Cameron has one more question. 1 moment. We're giving you 10 seconds, Cameron. He's phrasing it. Okay. When modeling a pedal, what is your comparison process like? How do you verify the accuracy?
Yeah. Well, there's a lot of different ways to do that. To me, I think the most important one is just listening and trying to compare how things sound. As I mentioned, I don't actually own a lot of physical hardware to compare to, so that can be kind of tricky for me. So usually I use Spice or something like that to generate, an approximation of what it should sound like in theory. Obviously, it'd be better if I had the real thing, but that can be expensive too. And then from there, so aside from just listening, there's a lot of different perceptual metrics that you could use. Usually for me, I've been kind of looking at what the machine learning folks are doing, because there's been a lot of research over the past, 5 years or so about how do we measure accuracy for audio signals in a way that is perceptually meaningful. So obviously, mean squared error is like the basic machine learning error function. But one that I've been using a lot is the error to signal ratio. So it's like the error divided by the total magnitude of the signal. And then you can do it over time. And then there's different weightings within that where you can weight the frequencies a little bit differently, again, based on sort of perceptually how we hear those frequencies. So that's usually my approach for verifying accuracy and things like that.
Yeah. Speaking of machine learning and neural networks for modeling. There is actually a hackathon happening this weekend. Not sure the details, but it's called the Neural Audio Synthesis Hackathon. That's happening this weekend, and I'm sure that if anybody has any interesting projects to propose, that they will accept them. So just look up Neural Audio Synthesis Hackathon. We do have another question, which is, can we use the WDF method for inductors to emulate the Nikola coil sounds?
I'm not familiar with that sound off the top of my head. One issue that I've run into with inductors, with wave digital filters, and with circuit modeling in general, is that it's pretty easy to do an ideal model of an inductor, but very few inductors behave ideally in the real world, which might be why they're not used particularly often in audio circuits. But like I was working with my friend Dirk a few months back on a model of the Pultec equalizer circuit. And we have a model that works that, assumes that the inductor is ideal. But one thing that Dirk really wanted to work on was sort of a more non-ideal model of the inductor and seeing how we could approach that. So yeah, I'm curious to see what's going to happen there. Dirk has a lot of really cool ideas.
Amazing. So I think that's everything for questions. Thank you very much.
Cool. Yeah.
That was a lot of fun. Yes.
And I'm also always very pleased when I see people using modern C++ for this kind of stuff. If you then move to C++ 20, you get even more stuff. You can use all kinds of different types as non-type template parameters, and you get more stuff to play with. So yeah.
Yeah, definitely excited for that.
Yeah. Anyway, thank you so much. I really, really enjoyed that and learned a lot.
Cool. Plays for the win.
Thanks, guys.
Yes. Great. Okay. I think it's a good time for us to wrap up. Yes. Thank you to Jatin, and also thank you to David, who unfortunately had a meeting, so he had to drop off. But thank you, David, for the really awesome talk on 80s game sound emulation with a high score. And thanks to our sponsors as well, Juice, Sonux, and Focusrite, for their support for the Audio Programmer Meetup. Once again, we're looking for talks. You can submit a talk on the Audio Programmer website, theaudioprogrammer.com/submit. And we hope to see some more submissions. Also, our community, which I think my link is broken, but it's theaudioprogrammer.com/community. And thank you to my co-host, Tamer, for being part of another.
Thank you, Josh. Always a lot of fun. I'm going to add a few more things, which is the next Audio Programmer Meetup is taking place, as you know, every second Tuesday of the month. So that's going to be the 11th of January, 2022, which then brings me to the second point, which is this was the last meetup of the year, which means I would like to wish you all a very Merry Christmas, if that is something that you celebrate, and also a very Happy New Year. Let's hope it's going to be a more awesome year than 2021. Which is not a very high bar, so I'm quite optimistic about that. And with that, anything else, Josh?
No, I think that's it. Yes, happy
right.
holidays to anybody who's celebrating. Happy 2021 and even a stronger 2022. Thank you very much, everybody, for joining us, and we will see you January 11th.
Yeah, and thank you very much for tuning in. Always a pleasure to be here. Thank you so much for listening, and see you in the new year. Bye, everyone.
New year. Bye, everybody.